Good morning, I'm Eleonora Pippia and today I want to present the work with Professor Tao Dang and Professor Alberto Policriti titled Image Approximation for Feed-Forward Neural Nets. In the last few years, the neural networks are increasingly being used in the development of control systems. We can think about robots, autonomous driving car or medical equipment. This trend encourages the use of the neural network also in more classical fields like closed-loop system. In this work, we want to focus on the neural net control systems, so systems in which the neural network plays the role of the controller. There are different tools that address the reachability problem when we have a standard system, so without a neural network. And if we have the neural network, we need to be able to approximate the behavior of the neural net. So, focusing on the neural network, we want to address the following problem. Given a neural network N and an input set X, we want to over-approximate the image N of X. And in this work, we want to do it using the Bernstein theory, so the Bernstein expansion for polynomial function. This is the agenda for today. I will start with the general idea behind our work, so with a high-level description. I will list the property for the Bernstein polynomial, and then I will go in detail on the first application that we decide to analyze. And finally, I will draw the conclusion, giving you the idea of what we want to do in the future. So let's start with a feed-forward neural network structure. We have an input, an output, an input set X, and then if we look at a single neuron, we have an affine function, so the weight matrix and plus the bias A, and then a nonlinear function that is the activation function. So in general, we have the output for each neuron that is described by a nonlinear function f of x. So if we focus on a layer L, we can say that the nonlinearity links the values at the previous layer with the values at the current layer. So in general, we can split the two functions, the affine one and the nonlinear one, and if the values at the previous layer, x to the L minus 1, are in a set that is defined by linear constraints, so a convex polytope, for example, this constraint must be propagated through the layer of the network. But first of all, we have a set of linear constraints thanks to the affine function. But the second step, that is the application of the activation function, creates a set of nonlinear constraints. So in the end, we need to be able to propagate the set A of nonlinear constraints that depends on the values x to the L minus 1 and x to the L. What we want to do is approximate the set A with a set A bar defined with linear constraints. Could be an hyperrectangle, but in this case we lose the input-output relation, or could be a polytope, so a convex, in general a convex polytope with linear constraints. As I told you before, we want to do it using the Bernstein theory, and the Bernstein theory works for polynomial functions, so we want to approximate the activation function, in general also with rational function, but we will see that in this case we are able to bound the image just with hyperrectangles or with polynomial function. Actually, we can do a little bit more. We can consider a piecewise polynomial function. For example, we can use a polynomial function in the slope, the blue part of the hyperbolic tangent on the left, and then a constant values minus 1 or 1 when the function is more flat. And this helps to reduce the polynomial degree. Let me give you a little bit of notation for the Bernstein polynomial. So consider a polynomial p of x in the power basis. We can define the Bernstein polynomial as follows, where the b of I are the Bernstein coefficient. In this expansion, the Bernstein coefficient have some important property. In particular, we will use these three. The sharpness, that means that some of the Bernstein coefficient match exactly the value of our polynomial function. The range enclosing that says that the maximum and the minimum Bernstein coefficient bounds the output of our polynomial function, or the convex hull. Well, each Bernstein coefficient corresponds to a single point in the domain, and this couple is called control points. The relation x, p of x, is bounded by the convex hull of all the control points, and this property holds for the unitary box. Let me give you an example to understand better this free property. We can consider the cubic p of x in the picture in the interval 0, 1. With the sharpness, we can compute two Bernstein coefficients, one in 0 and one in x equal to 1. If I compute all the others, so 4 coefficients, the range enclosing guarantees that the maximum and the minimum bounded the output values of our function. And finally, with the convex hull, we completely enclose the evolution of the polynomial function. This holds not just for the unitary box, but in a general hyperrectangle and also in simplices. Finally, the last property says that if we link with a piecewise linear function the Bernstein coefficient, we can bound the arrow that we commit using this approximation instead of the polynomial function. So coming back to the neural network N, in general we already said that we have a nonlinear function for each neuron, and the activation function can be a ReLU, a sigmoid on an hyperbolic tangent. These are the standard one. With the ReLU, we already know how to propagate the constraints layer by layer with a disjunction of linear constraints. What we want to analyze here is an approximation with rational function, and we know that we are able to approximate this free activation function with rational function. And as a case study, we will focus on the hyperbolic tangent. With the hyperbolic tangent, we have the Lambert infinite fraction that is an alternative way to define the hyperbolic tangent. If we stop this fraction after 2, 3, 4 fractions, we have an approximation of the function. And on the right, we can see how rapidly this approximation tends to the real function. The Bernstein theory that I described holds for polynomial function. What we can say about the rational function? Okay, the Bernstein coefficient can be computed in any case as the ratio between the Bernstein coefficient for the numerator and the Bernstein coefficient for the denominator. The range enclosing continues to hold for boxes and simplices, but first of all, the convex hull doesn't hold anymore, so we can bound the output just with hyperrectangles and not with the polytopes. And second, in order to use the range enclosing property, we need to be sure that the Bernstein coefficient of the denominator have all the same sign. And to do it, one way could be to split around the minimum or maximum of the function. In our case, so the Lambert fraction, the denominator is a positive function with a minimum in 0. Even if the function is positive, this is not a guarantee that all the coefficients are positive, but if we split around 0, in 0 the Bernstein coefficient match exactly the value of the function, so is a minimum, and then this is a guarantee that all the other coefficients are above, so positive. So the algorithm should work like this. We focus on a layer L, and we want to bound the output of a neuron I. So we have our rational function. First of all, we split around 0, so we obtain two sets x plus and x minus. If these sets are not boxes, we need to triangulate, so splitting simplices, because we are able to compute the Bernstein coefficients just with boxes and simplices. And then, finally, for each piece of the domain, we need to compute the Bernstein coefficient. and we collect all of them and we consider just the maximum and the minimum in order to bound the output with an interval. I also want to give you a faster algorithm that can be used when we don't need a really precise approximation, but this algorithm is really fast and scalable and take advantage of the monotonicity of the activation function and also the splitting of the two parts, the affine function, that is the first equation, and the activation function, that is the second one. The first one is linear. We just need to translate the domain into the unitary box, but the composition is again a linear function, so we can use the sharpness property to compute directly all the Bernstein coefficients. And this speeds up a lot the algorithm in the end. And we can consider again the maximum and the minimum to bound with an interval the intermediate output of this neuron. The second one is the activation function, that in the case of the hyperbolic tangent, but also with the sigmoid or the ReLU, is monotone, so we can directly apply the function within the interval to bound the result. We also decide to apply this last algorithm to an example. Here we have a single link robot arm, and this example is from Simulink, and we have a PID controller that is trying to follow the reference signal that is changing every 10 seconds. We train a neural net based on this controller and we obtain two neural networks. In the first case, we call it a neural network bad because it's not able to follow the reference signal minus 0.2, and this is the picture on the left. And then the second one is neural network OK because it's almost able to track, and is the picture on the right. So we decide to apply the previous algorithm to an hyperrectangle domain that is close to this case study. So we take the reference that is constantly minus 0.2. The y, that is the output of the system, is close to this reference up to a certain percentage of noise. And then the u, that is the output of the controller, follows the output of the system. And we obtain these intervals depending on the percentage that we allowed. And we can see that the approximate interval for the neural network bed is 2.4 times larger than the approximate interval for the neural network OK. And this is coherent with the behavior that we saw before. So this algorithm is really fast and can give actually an indication for the verification analysis. So in conclusion, we present a general approach to approximate a neural net, working layer by layer and actually neuron by neuron, and we decide to use the Bernstein theory to bound the output of each neuron. We go in detail analyzing the feasibility for the first case, that is the rational function, and we bound the output with intervals, so we obtain boxes and hyperrectangles domains. And also we exploit the monotonicity of the activation function, describing a faster algorithm to have a first intuition in the reachability analysis. So what we want to do in the future? First of all, we want to approximate the activation function with piecewise polynomial function in order to use the convex hull property instead of the range enclosing, and so to bound with polytopes. We want also to conduct an error analysis of our approximation. But what we want to really do is use this strategy just in the neuron in which we need high precision. So also sensitivity analysis can be useful to understand in which part of the network structure we need to focus, and maybe can be useful to integrate this methodology in an existing framework that could be Iran or whatever, and to include the methodology just in the neuron in which it's needed. Thank you for the attention.